Hello everyone, welcome to the Rapid Focus Revision Series by Excel Education Center. I am Lijo Joseph, I am teaching physics. And today we are going to see the topic moving charges and magnetism. And in this session, we'll be looking at different types of questions, the previous year MCQs and concept-based numericals. Hope you're all thorough with the theory. So let's not waste time, let's straight away get to the questions. Moving to question number 1. Two charged particles traverse identical helical paths in a completely opposite sense in a uniform magnetic field B is equal to B0 K cap. The options are, they have equal Z components of momenta, they must have equal charges, they necessarily represent a particle-antiparticle pair, the charge to mass ratio satisfies E by m of 1 plus E by m of 2 is equal to 0. Now let us see the concept here. Imagine you have three coordinate axes. These are called x, y, z. For convenience, I call this z axis. One of them is x, the other is y. Okay, now what if a charged particle enters this magnetic field? Just imagine a charged particle enters this magnetic field with a velocity v. Okay. It makes an angle theta with the z-axis. The magnetic field is on z-axis. It is given in the question, B0 K cap. Okay? And this velocity can be resolved into two components. The components are v cos theta, the component near to theta, and the other component is v sin theta. Whenever you have a vector, you can resolve it into two components. The component near to theta is cos component, the component away from theta is sin component. And the sin component causes the particle to move in a circle. It causes a circular motion, whereas the cos component drives the particle linearly in the forward direction. So what happens then? The combined effect is a helical path for the particle. So this path is called helical path. That looks like a spring. Okay, so there are two motions. One is the circular motion, second one is the linear motion. So the combined effect is a helical path for the particle. And the horizontal distance traveled in one rotation. By the time the particle makes one rotation, how much of horizontal distance is traveled? That distance is called pitch of the helix. Now how to find pitch of the helix? Pitch is given by v cos theta into time. Basically it is horizontal distance. Horizontal distance is horizontal velocity into time. Horizontal velocity multiplied by time will give you horizontal distance. And that is equal to v cos theta into the time taken for one rotation is 2 pi m divided by qb. You have learned this already. And this is called the pitch of the helix. And I'm going to get q by m on the left side. I get q to the left hand side. M is also taken to the left hand side. Then that will give me q comes here, m comes here. It is 2 pi into v cos theta over p into b. And as you can see, 2 is a constant, pi is a constant. Velocity is the same for both. One particle goes in this direction, whereas other particle goes in the opposite sense. Which means 2 is constant here, pi is constant here, v is constant, all other parameters are the same for both. So v is the same, theta is the same, pitch is the same for both. I said already that both will have same pitch because both travel identical helical paths as per the question. So 2 is constant, pi is constant, v and theta are the same for both the particles, one going from left to right, the other one going from right to left. Okay, and pitch is the same for both, magnetic field is also same for both because both enter the same magnetic field. So that would give me q by m is equal to a constant. Okay, and another thing is one particle goes to the right whereas other particle goes to the left. They are in opposite directions, which means Q by M of 1 should be equal to Q by M of 2 with a negative sign. Why that negative sign? Because one particle goes to the right, whereas the other particle goes to the left. Okay, so I'll get this to the left hand side. Q by M of 1 plus Q by M of 2 should be equal to 0. Now in the question they have called charge by the name E. So that must be E by M of 1 plus E by M of 2 should be equal to 0. Now let us check the options. Option A, they have Z components, equal Z components of momenta. You can see that it is wrong. Option B, they must have equal charges. That is also wrong because charge to mass ratio is the same, not charges. Option C, they necessarily represent a particle antiparticle pair, not necessarily. Antiparticle is what? For electron, the antiparticle is positron, whereas for a proton, the antiparticle is antiproton. Here, they are not necessarily particle-antiparticle pair. Basically, two particles with opposite charges. And look at the last option. That is E by M of 1 plus E by M of 2 is equal to 0. That is exactly what we got here. Q by M of 1 plus Q by M of 2 is equal to 0. So the correct answer is option D. Option D is the correct answer here. See the next question. Biot-Savart law indicates that the moving electrons velocity v produce a magnetic field such that B is perpendicular to V, B is parallel to V, it obeys inverse cube law, it is along the line joining the electron and the point of observation. So what is Biot-Savart law about? Look at this. We have a long wire on which you take a small element. So we have an element here. This is actually a current carrying element. Element is like a small segment with a length dl. You call it dl. The length of the element is dl. Okay, so it's a current carrying element and we need to find the magnetic field due to this element at a distance r. This point can be called P. I repeat, we have a long conductor carrying a current and there is a segment on the conductor which we call by the name dl. dl is a tiny segment which can be called an element. Now if I put an I in front of it, that makes it a current element. It is called a current element. This current element produces a magnetic field right at this location. What is the equation for magnetic field at that location? It is given by Biot-Savart law. According to Biot-Savart law, the magnetic field is given by mu 0 by 4 pi I dl sine theta divided by r square, where theta is the angle between the element and the line joining the center of the element and the point. Okay, so theta is this angle, I is the current passing through the wire, and r is the distance to that point. So if you rewrite this in vector form, it looks like this. Vector dB is equal to mu naught over 4 pi I into dl cross r divided by r cube. This is the vector form of Biot-Savart law. Okay, so what is the direction of that magnetic field? Look at this. You can find this mathematically because as per the rules of cross product, this should be in a direction perpendicular to both dl and r. Okay, direction of dB should be perpendicular to both dl and r. So dl is on the board, r is also on the board, so dl cross r must be into the board. dl cross r. You can use right hand rule to do this, right hand screw rule. Or so basically the magnetic field is into the board. Or there is another way to find this. Hold the conductor in your right hand, wrap your fingers around the conductor such that the thumb is in the direction of current. Look at that. The curled fingers would give you the direction of magnetic field. Where are they going? They are going into the board, right? Into the board. So basically, the magnetic field is into the board. Magnetic field is into the board. And the particle, electron, moves where? It's like current is moving up. That is similar to electron moving down, because current direction is opposite to the direction of electron flow. So if I assume that the current is going up, electron is flowing down. So electron flow is down and the magnetic field is into the board. They are perpendicular, right? Yes. Electron is flowing down. Electron is flowing down. It's on the board. Whereas the magnetic field is into the board. So electron is flowing on the board, downward. Magnetic field is into the board. On the board and into the board, they are perpendicular to each other, right? So what do they ask in this question? The moving electrons produce a magnetic field such that B is perpendicular to V. Magnetic field must be perpendicular to V. So magnetic field is into the board by the right hand grip rule. All right. You find the direction of magnetic field. It is into the board, as you can see. And then the electron flow is on the wire. Okay. So electron flow is straight down as per the figure. And the magnetic field is into the board. So they are perpendicular to each other. So magnetic field is perpendicular to V must be the correct option. Let's move to the next question. An electron is projected with uniform velocity along the axis of a current carrying solenoid. Which of the following is true? Okay. Option A, the electron will be accelerated along the axis. Option B, the electron's path will be circular about the axis. Option C, the electron will experience a force at 45 degrees to the axis and hence execute a helical path. Option D, the electron will continue to move with uniform velocity along the axis of the solenoid. Okay. So let us look at the question now one more time. Electron is projected. Where is it projected? It is projected with uniform velocity along the axis of a current carrying solenoid. So look at this. This is a current carrying solenoid. What is a solenoid? A solenoid is nothing but coils wound over a core, right? And when a current is allowed to pass through this, there is a magnetic field produced inside. What is the direction of magnetic field? I'll just draw them. The magnetic field is along the axis of the solenoid. If you remember, magnetic field is along the axis of the solenoid. Okay, for a solenoid, the magnetic field axis along the axis, and the magnetic field is given by mu0 times N by L into I. Mu0 is called permeability of free space. N is the number of turns and L is the length of the solenoid. Okay, and right into the solenoid, you're going to find what? You're going to shoot a particle. What kind of particle? An electron. So look at this electron. This is an electron that's being shot into the magnetic field, all right, along the axis. So the question is, what will happen to it? Right. It's a fundamental idea which you have learned in classes. You know, the force is given by, let's see what the force would be on the particle. The force is given by, magnetic force is given by QVB sine theta. A charged particle Q entering a magnetic field B with a velocity V at an angle theta. Remember, there are four things. Number one, it should be a charged particle. Number two, it should be moving with a velocity. Number three, it should be entering at an angle and entering a magnetic field. It will experience a force called QVB sine theta. This is called magnetic force. Okay, so let us see the situation here. Here the magnetic field is on x-axis. The particle also enters along x-axis. The magnetic field is on x-axis. Look at the blue lines here. And the particle also enters along the same direction, which means theta is equal to what? Theta is equal to 0. That means the particle enters along the direction of field, along the direction. Okay. So if theta is equal to 0, what is the force acting on the particle? QVB sine 0. and sine 0 is equal to 0, that is equal to 0. So the particle experiences no force at all. So let us see the question options now. The electron will be accelerated along the axis. That's wrong, because electron is not acted upon by any force. So no acceleration. No force, no acceleration. Correct. Let us look at the second one. The electron's path will be circular about the axis. That's also wrong. No force. Option C. The electron will experience a force at 45. That doesn't make any sense. Option D. The electron will continue to move with uniform velocity along the axis of the solenoid. Exactly. The electron will continue to move with uniform velocity, because if no force acts on the particle, the velocity will not change. That is what Newton's first law says, right? Every body continues to be at rest or in uniform motion along a direction unless it is compelled by an external unbalanced force. So, since no force is acting on the particle, you could say that velocity of the particle is a constant. So, particle moves with constant velocity along the same direction. So, let's see the option D. This is wrong. This is also wrong. Option D, the electron will continue to move with uniform velocity along the axis of the solenoid. Why? Because force is 0. Force is 0 means ma is equal to 0. But m can never be 0, right? Mass is a non-zero quantity. So acceleration is 0. Acceleration of 0 means what? Velocity must be equal to a constant. Constant. Okay. So correct answer is option D. Okay. Let's move to the next one now. A current carrying, this is slightly difficult. Current carrying circular loop of radius r is placed in the xy plane with center at the origin. Okay, current carrying circular loop of radius r is placed in the xy plane with center at the origin. All right, I'll just draw this. This is x-axis, y-axis. So I got the xy plane. This is x, this is y. Okay, and right in the middle, in the xy plane with center at the origin. So there is a circular coil whose center is at the origin, like this. Okay, there is a circular coil whose center is at the origin. As you can see, it's a circular coil. Okay, then half of the loop with x greater than 0 is now bent so that it lies in the yz plane. Okay, so you're going to bend this now, and then what are the options? The magnitude of magnetic moment now diminishes. Magnetic moment does not change. The magnitude of B at 0, 0, Z for Z greater than R increases. The magnitude of B at 0, 0, Z, Z greater than R is unchanged. So let us see the options. But before that, I'll tell you what is magnetic moment. For the circular coil, how to find the magnetic moment? Magnetic moment is written as current into area. Magnetic moment is equal to current into area. Now that is equal to, if I put vector sign on it, magnetic moment is equal to current into area into, what is the direction of area? Look at that. Just imagine that the current is going in anti-clockwise direction. You can put some random direction for the current, either anti-clockwise or clockwise, since they haven't mentioned anything. So how to find the direction of area? Direction of area, curl your fingers in the direction of arrow, then the thumb is pointed outward, right? Thumb is pointed outward. Okay, look at that. I'm just keeping my fingers in the direction of current, then the thumb is coming out of the board. Out of the board is called z-axis. To the right I've taken x, up is y, out of the board is z-axis. Okay, so z-axis means I can call it k cap. Because, I repeat one more time, x-axis is characterized by I cap, y-axis is represented by j cap. The magnetic field, the area here is along z-axis coming out of the board, it is k cap. Okay, now this is the first case. Now let us look at the second case now. Tell me what? Half of the loop with x greater than 0 is now bent so that it now lies in yz plane. What is x greater than 0? X greater than 0, this part. Look at that part, x greater than 0. X greater than 0 means to the right of this. X greater than 0 is here. X less than 0 is here. Why? X greater than 0 means to the right of origin. X greater than 0 means to the right of origin. X less than 0 means to the left of origin. Okay, so this region of the coil which is on the right side is bent so that it is in YZ plane now, like this. It is in this orientation right now, XY plane. I'm just bending it so that it looks, so that it is now in YZ plane, like this. So I'll redraw the figure now. Look at that. This is what it is now. I have this XY and this is Z axis. Okay, Z axis. Okay. So half of this ring is still intact. I don't touch it. All right. The other half is, so for this half, look at that. For this half, I'll write down the area. The area here is what? Area for this part. The new moment I'm writing, the new magnetic moment I'll write. Magnetic moment, the new magnetic moment is for this half, I'll write. Current is still I. Area is what now? A by 2, half of the loop, right? The entire loop had an area of A. Now it is half of it. So it is A by 2 into, what is the direction? Again, half of it now, half of it, it is coming out of the board itself. It's in the same plane. This half is still in the same plane. So for that, I can put not I cap, K cap. It is same as the old coil, right? Right, look at that. The direction of current is still the same. Direction of current is still the same, like the old one. We had like one more half here, no? Now, the direction is still the same. So for this part, the magnetic field is, or area vector is outward. So I into A by 2 into K cap. Plus, there is one more part now. Which part? There is one more part now. The other part is now bend, right? The other part is bend now. Where is it now? I'll tell you where is it now. See this? The other half is bent so that it is in this plane. So that it is in this plane. Look at that. In this plane. Like this. So for this, look at that. The magnetic field, the moment area vector is where? Area vector is to the right. So it was like this. Look at my palm here. Look at that. You know, it was initially like this. Now I've just bent one part of it in this direction. So look at them now. For this part, the moment is still the same. Area vector is in this direction. But for this part, the area vector is to the left. To the left. Or it is on x-axis. X-axis means I can put it what? I can put it as I into A by 2 into I cap. So I got the magnetic field, magnetic moment in the first case. This is what? Magnetic moment in the first case was I into A into K cap. I'll write them in the other board. Magnetic field in the first case. Magnetic field in the first case is, I'll write this. Magnetic field in the first case is M1 is equal to I into A into K cap. Am I correct? I into A into K cap. Yes. Magnetic field in the second case, magnetic moment in the second case has two components. One for the left half, the other one for this half. Okay. So I'll write them one by one. Keep this in mind. IA by 2 into K cap plus IA by 2 into I cap. Okay. Magnetic moment in the second case is IA by 2 into I cap plus IA by 2 into K cap. You know why? Because in the second case, like I said, half the coil is still on the same plane while the other half is on this plane. Okay, like this. It's bent over this way. Then I can find the magnitude of this now. What is the magnitude of a vector? How to find the magnitude of a vector? M2, magnitude of this vector is given by root of this component square plus this component square. Magnitude of a vector is given by this component square plus this component square. X square plus y square. What is the square of this? I square A square by 4 plus square of this I square A square by 4. So when you take the simplification, when you do the simplification, you get I square A square by 4 plus I square A square by 4 is 2I square A square by 4. Okay, let's get these numbers cut. It is 2. So what am I getting now? Take the square root. IA by root 2. Okay, look at the magnitude of first one. Magnitude of first one, that's a vector. Okay, it's also a vector. So magnitude of first one is what? Magnitude of first one is, first configuration is only I into A. This is the magnitude. This is the magnitude part. Okay, magnitude of first configuration is I into A, whereas magnitude of second configuration is I into A by root 2. If you put 1 by root 2, that is 0.707. Right, so that will give you 0.707 of IA. See this? So magnitude of second one is only 0.707 IA, whereas that of the first one is IA. Obviously, in the second case, magnetic moment has come down. So let's see the options now. Look at option A. The magnitude of magnetic moment now diminishes. Exactly, right. So that is the answer to the question. The magnitude of magnetic moment now diminishes. That automatically nullifies the second option because the magnetic moment does not change. That's wrong then. You can check the option C and D yourself. They are also wrong. Look at option A. The magnitude of magnetic moment now diminishes. See the situation one more time. Look at this. This is what it is. First coil, the magnetic moment is given by the entire coil. Magnetic moment is given by I into A. But as I said, you can assign a direction to it. How? This is the direction of current, and then thumb is coming out. Coming out means K cap. So I put IA into K cap. And when I break it into two, one half is this way, the other half is this way, right? So for this half, the magnetic moment is still coming out. That is why K cap. For the other half, the magnetic moment is on the x-axis, either I cap or minus I cap. Both are fine. We are looking at the magnitude only. All right. So for this one, the magnetic moment is coming out of the board. For this one, the magnetic moment is going to the right. So one part is K cap, the other part is I cap. Okay. So I've just rewritten them here on the inner board. So first one moment is what? I into A into K cap. If you look at the modulus or magnitude, it is simply I into A. But see the second case. For magnitude of second part, second configuration, it is IA divided by root 2, which is 0.707 IA. Okay. So if you compare first moment, which is IA, with second one, which is 0.707 IA, it is clear that the second one is less than the first one. All right. So magnetic moment diminishes. That should be the correct option. The magnitude of magnetic moment now diminishes. Okay. Let's move to the next one now. A charged particle moves through a magnetic field perpendicular to its direction. Then both momentum and kinetic energy of the particles are not constant. Both momentum and kinetic energy of the particles are constant. Kinetic energy changes but momentum remains constant. Momentum changes but kinetic energy remains constant. This is a very, very, very important question. I'll tell you how it should be done. First of all, when a charged particle enters a magnetic field, the force experienced is given by F is equal to QVB sine theta. Okay? The force experienced by a charged particle is QVB sine theta. What are the conditions? Number one, it should be a charged particle. Number two, it should enter a magnetic field. Number three, it should enter with a velocity. Number four, it should be entering at an angle, theta. Non-zero, non-180 angle. Okay. Now, this force may be written as F vector is equal to Q into V cross B. This is called the magnetic force. So, let's see the context one more time. We have a charged particle entering a magnetic field with a velocity V at an angle theta. So the particle is acted upon by a force. That force is called magnetic force. F is equal to Q into V cross B. Okay. And like I said before, as per the property of cross product, you learned this in dipole also, because in dipoles, electric dipole, there was a question once. If tau is written as P cross E, identify the pair of perpendicular vectors. That's a question from electrostatics. Vector tau is equal to vector P cross vector E. Vector tau is equal to vector P cross vector E. Okay. So in this case, this tau must be perpendicular to P, tau must be perpendicular to E. Why? Because by the rule of cross product, the resultant vector should be perpendicular to both the vectors. Look at this, you can use right hand screw rule. This is vector P, this is vector E, and where is vector tau? Put a screw right here, turn it in the clockwise direction. Turn it in the clockwise direction. Where would the screw go? The screw would go into the board, right? Look at that, this is vector P, this is vector E. Put a screw right at the junction, turn it like this, see where the screw is going. Look at that, it's perpendicular to P, right? It's perpendicular to E as well, right? So this is, if you learn mathematics, you know this. Anyway, cross product tells you that the resultant vector must be perpendicular to the component vectors. Okay, so by that rule, you could say that force is perpendicular to velocity. When force is, look at that, force is perpendicular to velocity, force is perpendicular to magnetic field also. So if force is perpendicular to velocity, such a force is called centripetal force. Centripetal force. You must have learned this before. Centripetal force. What is centripetal force? Whenever there is a circular motion, there must be a centripetal force acting. And what is that centripetal force? The name itself tells you, centripetal means center seeking, towards the center. Okay, you take a bucket of water, whirl that in a vertical circle like this. Okay, even at the topmost point, imagine you have a bucket with water. You expect water to fall down, but never. Water will never fall down. Because at the top of this, there is a centripetal force which keeps it in circular motion. Okay, so for circular motion, one thing is essential, centripetal force. Okay, you can check this out on YouTube. There is a stunt performed by Jaguar F-Pace engineers, drivers, test drivers. They did this looping the loop stunt. Now the car was driven in a loop. Even at the topmost point, the car wouldn't fall down. Because the weight of this car, or rather the normal reaction on the car, gives a centripetal force which keeps the car in circular path. Alright. You must have seen this in circus also. There is something called death globe. Okay. Alright. Anyway, this is what it is. Force acts as, the force is perpendicular to velocity, means it must be what? It must be a centripetal force. Centripetal force. Okay. Centripetal force. So whenever force is perpendicular to velocity, that force must be called centripetal force. Okay. Now, what is the work done by centripetal force? You learned it in first year classes. Work done is given by F into D into cos theta. F into D into cos theta. Work done is equal to F into D into cos theta. Okay. So this is a circular path. This is a centripetal force. This is the displacement tangential. Imagine you are driving a car and you had one bad day and you suddenly lose brake. What happens? You will skid off tangentially, right? Yes. Then what? The angle is 90 degrees, right? Yes. So you can put it right into this, Fc into D into cos of 90. So work done by the centripetal force is 0. So I have given you 2 points. The magnetic force acts as centripetal force. Centripetal force does 0 work, which means there is no work done in this case. Work done is 0 means change in kinetic energy is 0. So that is what work energy theorem says, right? Work energy theorem, work done is equal to change in kinetic energy. Imagine you are standing in the middle of a road and then a car hits you and you're flying off. Where do you get the kinetic energy from? The kinetic energy with which you are flying off is the work done by the car. Or in cricket, the kinetic energy with which the ball flies beyond the boundary is nothing but the work done by the batsman. So, if work is equal to 0, what does it mean? So, let's come to the conclusion now. Work is equal to 0. In this particular case, I've seen that the work is equal to 0. So, change in kinetic energy will be 0 or kinetic energy will be constant. Okay. Actually, this itself is a repeated board examination question for 2 marks. Show that kinetic energy remains constant for a particle entering a magnetic field. I'll illustrate the situation. Imagine you have a magnetic field. Okay. Magnetic field. This is into the board. Okay. And a charged particle is shot into this region, Q. Alright. So, it will have a path. This follows a path, right? Like I said, as it enters, it is acted upon by a force called magnetic force. What is magnetic force? F is equal to Q into V cross B. Q into V cross B. Where is it? Here, velocity is along the x-axis. Velocity is to the right. The particle goes to the right. The rightward direction is taken as I cap. Leftward is minus I cap. Upward is J cap. Downward is minus J cap. Outward is K cap. Into the board is minus K cap. So, magnetic field is where? It is minus BK cap. I can call it minus BK cap. So, if you put this in here, you will get the direction I cross K is minus J plus J. The direction as plus J. Look at that. I can put it right into this. Q into, what is it? Vi cross minus BK. So, this is QVB. I take the numbers out. I cross K is minus J. You want to know how? I cross K. Look at that. Look at that. This is I, this is J, this is K. If you go in the cyclic order, it's all positive. I cross J is K, J cross K is I, K cross I is J. Anticyclic order, it's all negative. I cross K is minus J. That's what I want. I cross K is minus J. But there is a minus already, no? So plus J. So what's my conclusion now? The direction of this magnetic field, direction of centripetal force is upward. Alright. The direction of centripetal force is upward. That means the center must be somewhere here. If that is to be the center, the particle should travel in a circular path like this. Okay. There is no change in kinetic energy. Then what else? I'll tell you what all things are not changing. Velocity, kinetic energy is constant here. Kinetic energy, constant. Kinetic energy remains constant. I have just proved it now. Okay. Then speed is a constant. Speed is also a constant. Why? Because kinetic energy is given by half into m into speed square. If kinetic energy is constant, speed is also constant. But what about velocity and momentum? Velocity is a vector quantity. So look at that. For vector quantity, how about the directions? How about the directions? Here the direction is this, direction is this, direction is this. So velocity continuously changes direction. Look at that. Velocity, here velocity is in this direction, in this direction, in this direction. So velocity continuously keeps changing because direction keeps changing. So velocity changes. I can say velocity is not a constant. In that case, momentum is mv, which is also a vector, right? That also changes. So this is such an important point, you know, you can expect this question this year, all right? I'll come back to this one more time. Even though it's a simple question, I've done too many things on this. All types of questions I've discussed here, okay? A charged particle moves through a magnetic field perpendicular to its direction. So let's have a quick recap. Both momentum and kinetic energy of the particles are not constant. Both momentum and kinetic energy of the particles are constant. Kinetic energy changes but momentum remains constant. Momentum changes but kinetic energy remains constant. So this is the situation. I started off this way. Like I said, when a charged particle enters a magnetic field, it is acted upon by a force. That force is called magnetic force. F is equal to QVB sine theta. Okay, so F vector, if I write it in vector form, F vector is equal to Q into VB sine theta is V cross B. AB sine theta is A cross B. So V cross B. And I also proved that in such situations, this force should be perpendicular to V, force should be perpendicular to B. Why? By the rule of cross product. Okay, when you take cross product, the answer should be perpendicular to both the component vectors. Okay, right. F should be perpendicular to V. So that is my conclusion now. F is perpendicular to V. So whenever force is perpendicular to velocity, you can call it centripetal force. Centripetal force. So basically, the magnetic force would always act as centripetal force. So what is the work done by centripetal force? Work done is given by force into displacement into cos of theta. So force into displacement into cos of 90. Look at that. Force is acting to the center. Centripetal force always acts to the center. Displacement is always tangential. Tangent. And angle is 90 degrees. You put it across, you're getting what? Work done is equal to 0. If work done is equal to 0, that would clearly imply that the change in kinetic energy is also equal to 0 thanks to work energy theorem, right? Because according to work energy theorem, the work done is nothing but the change in energy, right? So change in kinetic energy is equal to 0. So to summarize, whenever a charged particle enters a magnetic field, the change in kinetic energy is equal to 0. They'll ask you to prove this. It's an important question. All right, descriptive question. And then I have my conclusion, change in kinetic energy is 0, which would clearly confirm that kinetic energy is a constant. Change in kinetic energy is 0 means kinetic energy is constant. If change in my weight is 0, that would mean that my weight is constant. If change in my salary is 0, that means what? My salary is constant. So if change in something is 0, that means that quantity is a constant. So here kinetic energy is a constant. So I have my conclusion now, kinetic energy is a constant. If kinetic energy is constant, half mv square is constant, half mv square is constant, half is already constant, m is already constant, and v square, speed must be constant then. So kinetic energy is constant, speed is constant. Now if you look at this scenario, you will understand that velocity and momentum will keep changing. Why? Look at this. I have just traced the path of the particle. Okay, because in the past they have asked to trace the trajectory of the particle. This is how you do it. You write the velocity. Where is velocity? Look at that. The particle goes to the right as per my question. So V is equal to Vi cap. The rightward direction can be called I cap. Okay, V is the magnitude. And magnetic field is into the board. Into the board is called what? Into the board is minus K cap. Right word is I cap, left word is minus I cap. Upward is J cap, downward is minus J cap. Outward is K cap, inward is minus K cap. So magnetic field is minus BK cap. Okay, so I can put it into my equation for force. It is Q into V cross B. That is Q into Vi cross minus BK. I get Q, V, B out. They are all constants. And I cross minus K. Look at this. I cross minus K. It's minus J. You're going in the anticyclic order. So it's minus J, no? But there is already a minus sign waiting. So minus or minus is plus, plus J. So what is my final conclusion? The force is acting in J cap direction. J cap means Y axis, upward. J cap is upward. Minus J cap is downward. So now I'm certain that the force is acting in the upward direction. Alright, this is the direction of magnetic force, which is also the centripetal force. Okay, and you know one thing, centripetal force must be acting to the center. So center must be somewhere here. Okay, So if that is to be the center, the particle should take a curve this way. Okay. Now had I got minus j cap, I would have drawn the arrow down, the center would have been here, and the particle would have taken a path like this. Okay. So this is the path of the particle. Now what? Look at this. At all points, the tangents are in different directions, right? Here, the velocity is in this direction. Here, it has another direction. Here, it has yet another direction. So the direction keeps changing, which would actually make velocity to change continuously. And if velocity changes, momentum also must change, because momentum is also a vector quantity, mass into velocity. So to cut it short, we have four things. Kinetic energy is a constant, speed is a constant, velocity keeps changing, and momentum also keeps changing. Now let us look at the options. Look at option D now. See what is option D? Momentum changes but kinetic energy remains constant. Momentum changes but kinetic energy remains constant. So the answer is option D. Let's move to the next one now. The magnetic dipole moment of a current carrying coil does not depend upon. That's an easy one, but it's a Cbse paper question. Magnetic dipole moment of a current carrying coil. What is the equation for magnetic dipole moment of a current carrying coil? It is given by NIA. Imagine the coil has N turns. Look at this. It has N turns like this. How to find the dipole moment? Magnetic moment? Magnetic moment is given by N into I into A. N is the number of turns. I is the current passing through the coil. A is the area of the coil, okay? So if you look at it, the magnetic dipole moment of a current carrying coil does not depend upon number of turns of the coil. No, it depends on the number of turns, right? Cross-sectional area of the coil. It depends on the cross-sectional area as well. And the third one, current flowing in the coil. Yes, it has dependence on current as well. And look at the last option, material of the turns of the coil. You don't see any term that's related to material of the turns of the coil, right? So, number of turns, current, area, these are what? Number of turns, current, area, these are the factors which would affect the magnetic moment. Am I correct? So, in that case, the answer would be, they are asking what? The magnetic dipole moment of a current carrying coil does not depend upon material of the turns of the coil. Answer should be option D. That's an easy one. Okay. Let's get to the next one now. An electron is released from rest in a region of uniform electric and magnetic fields acting parallel to each other. Electron is released from rest in a region of uniform electric and magnetic fields acting parallel to each other. So electric and magnetic fields are acting parallel to each other. I'll draw the electric field lines first. Electric field line. This is electric field line. The yellow ones are electric field lines, okay? And the magnetic field line is represented by the orange one. Look at that. The magnetic field line, the magnetic field line. Okay? So the electric field line is represented by the yellow arrows, whereas the magnetic field lines are represented by the orange arrows. And what is the context here? An electron is released from rest. You are putting an electron right inside. This is an electron. And what will happen now? Look at that. There are two fields, right? One is electric field, the other is magnetic field. Okay, so these fields are acting parallel to each other. Parallel means what? Look at that, I have just drawn it that way only. The lines are parallel to each other, right? And then what? Let us see the magnetic force first. What is the magnetic force equation? QVB sine theta. Whenever a charged particle moves in a magnetic field with a velocity v at an angle theta, it experiences a force QVB sine theta. Alright. Here, this will experience what? It will experience zero force. Why? Because this particle is released from rest. So it is not moving at the moment. Still, if it is moving, theta would be zero. I'll tell you why. Let us calculate the electrostatic force. What is electrostatic force? Electrostatic force is given by QE. Okay, so this particle will have an electrostatic force. In which direction? The direction of electric field lines is the direction of positive charges. So this direction of electric field lines would give you what? The direction in which positive charges would move. So where would negative charge move? Opposite to it. Correct. If positive charges are moving along the direction of electric field, you know this for sure, negative charge would move in the opposite direction. So this particle, this electron, will be moving in the opposite direction. Right. By which force? By the electrostatic force. According to the equation for electrostatic force, F is given by Q into E. Q into E. But as you can see, it is to the left. Why is it to the left? Because it's a negative particle. Positive particle would have moved in the direction of electric field, whereas negative particle moves in the opposite direction. So that is why it's moving to the left. Now let us see the magnetic force. Magnetic force is given by what? So now we know that by the electric force, the particle moves in a straight line to the left. Straight line to the left. What is force now? Magnetic force now, QVB sine theta. That is equal to charge of electron minus E. Velocity V. Magnetic field B. Sine of theta is 180. Why is it 180? Because I've drawn the magnetic field to the right and the particle moves to the left. They are in opposite directions, right? Anti-parallel, right? This electron is moving anti-parallel to the magnetic field. So theta is 180. Sine 180 is what? 0. So in short, only the electric field plays a role here in the movement of electron. And it causes what motion? Straight line motion. So let us look at the options. Move in a straight line, move in a circle, remain stationary, move in a helical path. Obviously, it will move in a straight line because the particle, I'll recap it one more time. Look at this. Electrostatic force causes the particle to move in a straight line. So now it is moving. So it must be acted upon by a magnetic force. QVB sine theta. But as you can see, theta is 180 here. Alright, it is moving to the left, whereas the magnetic field is to the right. So angle is 180, 180. One is to the left. Look at that, the particle moves to the left. The orange line is to the right. Angle is 180. Sine 180 will be equal to 0. So magnetic force is not acting on the particle. Only electric force is in action, which means the particle will move in a straight line. Okay, a straight conductor. Next question. A straight conductor carrying a current. A straight current carrying conductor is placed inside a uniform magnetic field. Okay, the force per length acting on the conductor is. Okay, so we have a uniform magnetic field again. Look at this. This is the uniform magnetic field. Uniform magnetic field means all the lines are parallel, all the lines are equidistant, equally spaced. Okay, so this is called a uniform magnetic field. And right inside, you have kept a conductor. Look at that. You have kept a conductor. What sort of conductor? It's a current carrying conductor. Look at that. It carries a current carrying conductor. And it is placed at an angle theta. What happens now? This is a current carrying conductor placed inside a magnetic field. Okay. And current is actually what? Current is caused by the flow of electrons. So actually there are billions of electrons in motion inside the conductor. So inside the conductor, electrons are continuously flowing, right? And each electron will have a force on it. What force? We've been seeing since beginning now, right? Each electron is acted upon by a force called magnetic force, QVB sine theta, QVB sine theta, QVB sine theta. Every single electron will be acted upon by this magnetic force. What is the net result on this conductor? This conductor as such will have a force. The conductor will be thrown off in a particular direction. Alright. Anyway, that force is given by ILB sine theta. Okay. So that is the context here. A straight conductor straight current carrying conductor is placed inside a uniform magnetic field. The force per length, look at that, the force per length is the question. Force per length, let us take length to the left hand side because they are asking force per length. What is force per length? IB sine theta. Okay, force per length is, they say maximum, minimum, maximum, minimum. See the options. Option A, maximum when the conductor is perpendicular to the direction of magnetic field. Okay, maximum when the conductor is along the direction of magnetic field. Minimum when the conductor is perpendicular to the direction of magnetic field. Then minimum when the conductor makes an angle of 45 degrees to the direction of magnetic field. Okay, so they say like maximum, minimum, maximum, minimum. Let's look at this. When do we have maximum for this? In order to have maximum, this function should be what? Sine theta should be what? Sine theta should be 1. So if you want to have maximum value for this, that sine theta should be 1. Sine theta is 1 means what? Theta should be 90. That means the force is maximum, or rather the force per length is maximum when sine theta is maximum. Sine theta is maximum when theta is 90. Theta is 90 means what? The conductor is perpendicular to the magnetic field. Okay, so that is our final conclusion. The force is maximum or force per length is maximum when the conductor is perpendicular to the magnetic field. Let us look at it. Force per length is maximum when the conductor is perpendicular to the direction of magnetic field. So answer should be option A. Hope it's clear. Let's move to the next one now. Next question. A region has a uniform magnetic field in it. A proton enters the region with a velocity making an angle of 45 degrees with the direction of magnetic field. In this region, the proton will move on a path having the shape of. Okay, we have already done this, but I'll tell you one more time. Look at this. I have like 3 axes, x axis, y axis and z axis. See this? Z axis. Alright, x, y, z. Then what? We are just shooting a particle into this at an angle with a velocity theta. Tell me what? There are 2 components, right? One component is v sine theta, like we saw in the first question. And second component is v cos theta. And what do? This cos component will cause a linear motion, whereas the sine component will cause a circular motion. So this particle will execute a circular path, plus that will push it to the right, which will make it a spiral path like this. Alright, when both the components are in action. Alright, so when this theta is a non-zero, non-90 angle, any angle other than 0 and 90, in between 0 and 90, both the components will be alive, which means there will be both linear motion and circular motion. So the path of the particle will be helix. Okay, so look at the question again. The particle enters the magnetic field at an angle of 45 degrees. So it is entering at an angle of 45 degrees. So both the components will cause circular motion as well as linear motion. So the combined effect will be a helical path. This is valid for any angle between 0 and 45, 0 and 90 degrees, except for 0 and 90. So let us see what happens. So for this question, the answer is helix, because the particle enters at 45 degrees. At 45 degrees, this component will be v cos 45. The other component is v sin 45. Both are in action. Correct. But what if it is entering at an angle 0 degrees? 0 degree. Case number 1. 0 degree. Theta is equal to 0. Let's see the components now. V cos theta is equal to v cos 0. Cos component, okay? V cos 0. Cos 0 is 1. That is v. V sin theta is equal to v sin 0. Sin 0, 0. It is 0. So, what do you understand from this? The sine component is dead. It's no more there, right? It's gone, right? So, sine component is no more in action. Only cos component causes a motion for the particle, right? Cos component causes which motion? Linear motion. Cos component causes linear motion. So the path of the particle will be what? In this case, the path of the particle will be linear. The path of the particle will be linear. Okay, linear. For which case? Case number 1, theta is equal to 0. Now let us look at the other case. Imagine the particle, this is valid for even 180. Okay, same thing, theta is equal to 180 also. The particle enters parallelly or the particle enters anti-parallelly. Alright. Now question number 2, case number 2, if the particle enters perpendicularly, theta is equal to 90. Tell me what's going to happen. Look at that. It is V cos theta. It is V cos 90. Cos 90 will be 0. Right. Cos 90 is 0. So, V cos theta is 0. How about V sin theta? V sin theta is V sin 90. Sin 90 is 1. So, it is V. So, look at that. This time around, the cos component is gone. Only the sine component survives. Alright. Only the sine component survives. Sine component causes what kind of motion? I told you sine component causes the magnetic force, which is acting as centripetal force. Right. So, the sine component eventually causes a circular path for the particle. Circular path. So, in this case, the path of the particle will be what? The path of the particle will be circular. Okay, it's a previous Cbse question asked in 2020, but I would pick this as one of the most important questions in this chapter. All the 3 cases. The particle enters parallelly or anti-parallelly. Theta is equal to 0, theta is equal to 180. The particle moves in a straight line path. The path of the particle is linear. If the particle enters perpendicularly, that is theta is equal to 90, the particle executes circular motion. But in the case where the particle enters at any angle other than 0 and 90, starting from 0 to 90, other than 0 and 90, the particle has both sine component and cos component on it, then what? It will have a helical path. So that is what the question is. Eventually the path of the particle will be helix. So answer is option D. Okay, now let's move to the next question. A long straight wire of radius A carries a steady current I. The current is uniformly distributed over its cross section. The ratio of magnetic field at A by 2 and 2A is. Okay, so I'll draw the figure here. This is the conductor you are talking about. Okay, I have a conductor here, right, like this. This is a long conductor, okay, infinitely long conductor. Alright, and this is the axis of the conductor. Right in the middle, it has an axis of the conductor, okay, right? Oh, it's not in the middle. Anyway, right. So long straight wire. This is a straight wire, but it's like an exaggerated view. It's like a solid cylinder. Then what? It has a radius of A. It carries a steady current I. The current is uniformly distributed over its cross section. The current passes through the entire cross-sectional area. Then the ratio of magnetic field at A by 2 and 2A. Where is A by 2? A by 2. A is the radius, right? A is the radius. So A by 2 must be? A by 2 must be an inside point, right? A by 2 must be an inside point. Because A is the radius of the cylinder. Radius of the cylinder. A by 2 means half the radius. So it must be an inside point, right? The ratio of magnetic field at A by 2 and 2A. Where is 2A? 2A is, this is A, this is A. This is 2A. Look at that. This is 2A. So that is an outside point. So basically they are asking the ratio of magnetic fields at an inside point and an outside point. I call them P and Q respectively. Alright. So I repeat one more time. We have a current carrying conductor. This is a long current carrying conductor. Alright. And we have an inside point for the conductor as well as an outside point. Okay. And in this question, they are asking you to find the ratio of magnetic fields at 2 points. Which are the points? One is A by 2, second is 2A. A by 2 is inside point, 2A is outside point. Okay, actually it is solved in the reader. It's given in the blue box. It is done, this derivation is done using Ampere's circuital law. You even learned the graph for this particular case. Inside the conductor, the graph is straight line, whereas outside the conductor, it is a rectangular hyperbola. The magnetic field against distance graph. This graph is very, very, very important for board examinations, okay? The magnetic field inside the conductor is a straight line, whereas magnetic field outside is rectangular hyperbola, inverse proportionality. But I'll tell you the equations now. Magnetic field at P. Magnetic field inside is given by, this is the equation for, I'll write magnetic field outside first, okay? Magnetic field outside. Magnetic field outside is given by mu 0 I divided by 2, mu 0 by 4 pi into I by R into 2, mu 0 I by 2 pi R. This is the equation for magnetic field outside. Mu 0 I by 2 pi R. Mu 0 I by 2 pi R. Magnetic field outside is given by mu 0 I divided by 2 pi R. Okay, so let us write the outside point. I call it by the name Q. So BQ is equal to mu 0 I divided by 2 pi into R. R is actually the distance to that point. What is the distance to the point? Distance to the point is, for the outside point it is 2a. Distance to the point is 2a. From the axis of the conductor to that point, distance is equal to 2a. Correct? So that is my equation number 1. Now I'll write the second case, the magnetic field inside. Magnetic field inside, I'll write it. There is an easy way to memorize it. Write the same equation, mu 0 I by 2 pi capital R, make it capital R, then put an extra R on the numerator, small letter r, and extra R on the denominator. It looks like the same equation, mu 0 I by 2 pi R, only thing is that it's capital letter R, then I put one R on numerator, capital letter R on denominator. You better learn this equation by heart. So what is magnetic field at Q now? It is inside, right? Oh no, magnetic field at P. Magnetic field at P. P is inside point, okay? Mu 0 I into R is distance to that point, small r. Small r is distance to that point. Distance to that point is a by 2 by 2 pi r square, the radius square. What is the radius of the conductor? Radius of the conductor is a square, a. Capital R is radius of the conductor. That is equation number 2. Now I'm being asked to find outside to inside, right? Ratio of inside to outside. Okay, a by 2 to 2a. So inside point to outside point. So BP divided by BQ. What am I going to get? Let's check it out. BP by BQ. What is BP? Mu 0 I a by 2 by 2 pi a square. Oh, I'll write it. Mu 0 I a by 2 by 2 pi a square by mu 0 I by 2 pi into 2a. So let's cut them out. I'm going to cut the common terms. Mu 0 cuts. 2 pi also gets gone. Then I is gone. Then this becomes what? The 2 comes to denominator, okay? A is also cut there. So that is leaving me with, on the numerator, there is a 2 that's coming to denominator. 1 by 2a. Look at that. This 2 comes to denominator, 1 by 2a. And here also I have 1 by 2a. And you know what happens now? They are also getting cut, leaving you with 1:1 as the correct answer, correct option. Is that there in the options? 1 by 1? Yes, option B is correct. Option B is correct. Okay, that's an important question. You can expect same question in descriptive side also. It's very important. Okay, let's move to the next one now. See this, a rectangular loop carrying a current I is situated near a long straight wire such that the wire is parallel to one of the sides of the loop and is in the plane of the loop. if a steady current is established in the wire as shown in the figure, the loop will. The figure is not clear here. I'll just draw the figure. Okay, right. So we have like, I'll just illustrate the situation. We have a conductor here. Okay, we have a conductor here. Look at this. We have a conductor. This is a straight conductor. It carries a current I. All right. And right next to it, we have a loop. Look at the loop. This is a square loop. Okay, this is a square loop. All right. It carries another current, say I dash or I1. All right. That current goes through the circuit to come back, right? And let us name it like A, B, C, D. Okay, so this is the context now. I repeat, we have a current carrying conductor. Right next to it, you have kept a circular coil. Oh, sorry, rectangular coil. Okay, or rather a square coil. Okay, now this has come many times in examinations. They would even ask you to calculate the torque on it. You can prove that the torque is equal to 0, right? And you can even calculate the force. But here, they are not asking you to find the force. They are simply asking whether it will rotate about an axis parallel to wire. That's absolutely wrong. Torque will be equal to 0. I can prove it. Move away from the wire, move towards the wire, remain stationary. So let's look at the situation one more time. See this? Now, here, if you look at it, these two wires will have forces. You know, this conductor creates a magnetic field here. All right, on the right side. You keep your conductor in your right hand, thumb is in the direction of current. Okay? The curled fingers will give you direction of magnetic field. Look at that. To the right of it, it's going in, and to the left of it, it is coming out. Okay? So on the right side of the conductor, the magnetic field is going into the board, 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 into the board. Okay? Okay. Now, if you can calculate the force on this conductor, you will see that it is IBB in this direction, and on this conductor it is IBB in this direction. Those forces are equal and opposite. Why? Because force is given by ILB sine theta. Force is actually, this loop is placed where? In the magnetic field created by the first conductor. The loop is situated in the magnetic field created by the conductor. Okay. So each conductor experiences a force. That's what my point is. Okay. But if you look at it, the length of this conductor I call B, small letter b. Okay. This is also small letter b. This is L. This is L. Okay. Right. So if you look at this force, this conductor, top conductor, the force on it is straight up. How did I find? Just try taking I into L cross B. I into L cross B. Okay. I into B cross B. It is I is to the right, so I cap. Magnetic field is inward, so minus K cap. So it will be like, turn the screw, it is going up. Okay, you can find it. You want me to do? I'll do it. Okay, F is given by I into. What is the direction of B? It is to the right, so BI cap. What is the direction of magnetic field? Into the board. Into the board is minus K cap. So that will be I, B, B into I cross K is minus J. I cross K is minus J. But there is a minus already, no? So it is, which is plus J now. So that is why the direction of force is upward. Similar way the direction of force is downward. So what's my point there? Those forces are going to get cancelled out no matter what it is. In all such situations, the top conductor will have a force IBB. The bottom conductor will have same force IBB down. They'll cancel out each other, right? Correct. Then look at these two conductors. What about the forces on them? I'll just draw them. I'll just write them. Force on the conductor AB. Look at that. Force on the conductor AB. See this force? What kind of a force is this? Look at the currents. This current is going up. This current is going up. They are like currents, right? Like currents. Like currents. Like means traveling in same direction. Like poles repel, north pole and north pole repel, south pole and south pole repel. Correct. Magnets. Okay. Like charges repel, positive and positive repel, negative and negative repel, but like currents attract each other. Like currents attract each other. Okay. So these currents are like currents. So the force on it is attractive. That force on AB is what? What kind of a force is this? It is attractive. Okay. So force on the conductor AB is attractive. Why is it attractive? Look at that. This current is going up. This current is also going up. So they are parallel. They are in the same direction, which means they are like currents. Like currents always attract each other. Like currents always attract each other. All right. Now let us look at force on CD. What is force on CD? Look at that. This current is going up. Conductor. Current on the conductor is going up. Current on this conductor is coming down. Look at that. CD. It's coming down. That arrow is down. Down, down. This is going up. So they are unlike currents. Unlike charges attract, unlike poles attract, but unlike currents repel each other. So this conductor and this conductor will repel each other. Look at that. That force is repel. Repulsive. Right. Repulsive. Now, what is the net force of these two? I have intentionally drawn this vector longer than that vector. Why? Because force is stronger on this conductor, right? Why? Magnetic field is stronger there. Why? Because that's closer to the source wire. When you go closer to an AC, cooling is more, right? Or if you go close to a heater, heating is more. Same way, this conductor is closer to this conductor, no? The source of magnetic field. So this force will be stronger than that force. Okay. So this conductor will be acted by a stronger force. Look at that. It's a stronger force. I'll put a much bigger arrow. Look at that. Stronger force. But the poor guy, the other guy has like weaker force because it's like far away. It's at a farther location, no? From this wire, it is at a farther location. So that force is weaker than this force, right? So who will win eventually? Obviously, the stronger force will win. Who is the stronger force? Attractive force. So the net force will be what now? In the fight between these two forces, eventually this guy will win. So net force is what? Net force is attractive. Okay. So net force is attractive means what? This loop will move towards the wire. This loop will move towards the wire. So let's see the options. As shown in the figure, the loop will move towards the wire. Answer should be option C. And the same question has come in discrete part also. You'll be asked to calculate the net force. It's a 3-mark question. You'll be asked to calculate the net force. You can find ILB here. You can find ILB here. But those ILBs will be different because magnetic field here and magnetic field here are different because that point is at a farther location. No, you have to find them separately and then find the net. Okay, and you can even show that the torque is equal to 0. Torque is equal to 0. Both are asked together in a paper, in a question, and that's a 3-mark question, previous board question. All right, it's very, 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 very important. I expect that question this time. It's so important, okay? But for solving this question, you don't need to do that. You can directly use the concept here. What is it? Look at that. The force on the top conductor is straight up. Force on the bottom conductor is straight down. And they're going to get cancelled with each other. Okay? But force on the left conductor is to the left. Why? Because these are like currents. Like currents would attract each other. Force on the right conductor, these are unlike currents. Unlike currents would repel each other. All right. So on this conductor, the force is attractive. On this conductor, the force is repulsive. But the stronger force is attractive. Why? Because this conductor is closer to the wire, which produces the magnetic field. So this wire is sitting in a stronger magnetic field, okay, than the other one. So attractive force is stronger this time. So when you take the net, the effective force will be attractive. So the loop, this loop will have an attractive force towards it. The loop will move towards this conductor. So the answer is the loop will move towards the conductor, move towards the wire, option C. So let's look at the next question now. An isosceles right angle current carrying loop PQR is placed in a uniform magnetic field B pointing along PR. So the magnetic field lines are along the upward direction. Alright, PR. If the magnetic force acting on the arm PQ is F, the magnetic force acting on PQ is F. Then the magnetic force which acts on the arm QR will be. You have to find the force on this arm. Okay. It's a Cbse 2020 paper question. I'll tell you how to do this. First of all, you need to know one thing, that the magnetic field, if you're keeping a coil in a magnetic field, uniform magnetic field, the net force on the coil is equal to 0. If you place a loop in a magnetic field, uniform magnetic field, the net force on the coil will be 0. Okay, so what is the net force here? Force on PQ plus force on QR plus force on RP. Okay, there are three components for force. Number 1, force on PQ. Number 2, force on QR. Number 3, force on RP. So I can write force on PQ plus force on QR plus force on PR should be equal to 0. And they have given a couple of things here. Force on PQ is given as capital letter F. Force on PQ. Look at that, it is given. Force on PQ is given as what? Capital letter F, right? So I can put force on PQ as capital letter F plus, what is force on RP? Look at that. RP is straight down, magnetic field is straight up, the current is going in this direction, right? IL, current is going, just imagine the current was going to the right, then it was going up and coming down. So look at that, the current is going down, magnetic field is straight up, they are anti-parallel, right? If they are anti-parallel, what is the force acting? Force acting is given by ILB sine 180. Because force acting on a conductor is given by ILB sine theta. Force acting on a current carrying conductor in a magnetic field is given by ILB sine theta. Here, the magnetic field is going up, it's straight up, pointed upwards. The current is going downwards. They are anti-parallel, so theta is 180. That would make what? The force on that conductor equal to 0, because sine 180 is 0, right? Sine 180 is 0, right? So force on RP is, this is in fact force on RP. Force on RP. So force on RP or force on PR, the last one, is equal to 0. Is equal to 0. This is force on QR. They are asking you to find force on QR. How to get force on QR now? Get this to the right hand side, that will be minus F. Force on QR is equal to minus F. Answer is option D, minus F. You can do this by another method. You can directly take ILB sine theta, where this length will be, you can take 45 here, sine theta is 45 because it's a right angled isosceles triangle. This side is L, this side is L, so that side will be root 2L. Okay, so ILB sine theta, you try that method, you will get the answer then. Okay, I into root 2L into B into sine 45. That also will give you the same answer. And as current goes in this direction, this one was in this direction, this one is in this direction, opposite. So that must be minus F. You can try the alternate method yourself. Did you understand the alternate method? I will tell you one more time if you didn't understand. Alternate method for finding force on this is directly using ILB sine theta. I into length is root 2L. Why root 2L? Pythagoras theorem. Root of L square plus L square. Okay. Yes. Into. Yeah. Then magnetic field into sine of 45. The angle is 45 degrees. You can put it there to find the force. But anyway, this method is much better anyway. Force on QR is equal to 0. So I'll tell you one more time. This is a loop. A loop is placed in a uniform magnetic field. In a uniform magnetic field, if you place a loop, the net force acting is equal to 0. So net force is actually due to the contributions of three forces: force on PQ, force on QR, force on RP. So force on PQ plus force on QR plus force on PR is equal to 0. Force on PR is equal to 0 here. Force on PQ is given, it's given as F. Force on PQ is given as F. So F plus FQR is equal to 0. Get this right hand side, FQR is equal to minus of F. See the next one. A current of 10 amperes is flowing from east to west in a straight wire kept on a horizontal table. The magnetic field developed at a distance of 10 centimeter due north on the table is. Okay. So we have a table here. This is a table. All right. So we have like a table and then a wire is passing over it. Look at that. A wire is passing over this. All right. The wire is carrying a current from east to west. So this side is east and this side is west. So the current is flowing from east to west. Okay. And then what? Look at that. On the table you have kept a wire. The wire carries a current from east to west. East is on the right side, west is on the left side. Okay. Right. And on the other side of the wire it is north and this side of the wire is south. All right. That side is north, this side is south. Okay. And the magnetic field developed at a distance of 10 centimeter due north on the table is. It is an infinitely long wire for which the magnetic field is given by mu 0 I by 2 pi r. This is the equation for magnetic field due to an infinitely long wire. Mu 0 by 4 pi into I by r into 2. Infinitely long wire, right? Yes, mu 0 by 4 pi into I by r into 2, or it is mu 0 I divided by 2 pi r. So I put the value here. Mu 0 value is 4 pi into 10 raised to minus 7. The current flowing is 10 amperes divided by 2 pi into r is the distance 10 centimeters. 10 into 10 raised to minus 2. Why 10 raised to minus 2? Centimeters is to be converted to meters. Centimeters is to be converted to meters. Now what? Let's get the common terms cut. This 10 gets cut with the 10. 4 pi and 2 pi cut, you're getting 2. So finally you're getting what? That is equal to 2 into 10 power minus 7 with 10 power minus 2, 10 power minus 5 Tesla. This is the value of magnetic field. But there is one more part to it, because there are two options with 10 power 2 into 10 raised to minus 5. Correct. So our correct answer should be of either option A or B. Option C and option D are ruled out. They are 4 into 10 raised to minus 5, right? So this is gone, that is also ruled out. Now between them, whether it is acting up or down, that is what my question is. Look at that. The magnetic field developed at a distance of 10 centimeters due north on the table. Where is north? North is on that side, south is on this side. This is north, this is south. Okay. And how to find the direction of magnetic field? Look at this. You keep the finger in the direction of current. Other fingers, look at that. It's going on the other side. On the other side of the wire, it's going down, and on this side of the wire, it's coming up. Look at that. You hold it this way. Look at this. This is the wire. You hold it this way. Here, it's going down. On that side of the wire, it is going down. On this side of the wire, it is going up. So it's like this. I'll just draw a line. See this? This is how I draw it. On that side, it's going. Look at this. This is my thumb. Thumb is in the direction of current. That's going down. So there it is going down, and it is going up here. On that side it is going down, and on the left side it's going up. Look at that. So if you're going to the right, on the right side it's going down, here it is going up. Okay. Look at that. You hold it on the right, you hold it in your right hand. Just wrap the fingers around the wire. Thumb gives you the direction of current. Look at that. It is going down. The fingers are going down. There the fingers are coming up. Look at that. The fingers are going down. All right. So on that side, the magnetic field is pointed downward. So the correct answer is 2 into 10 raised to minus 5 Tesla, acting downwards. Do let me know in the comment box if you understood or not, okay? I can help you with it later then. Alright, so on the right side it is down, on the left side it is up. You can use right hand rule to do this. Alright, just imagine the thumb is in the direction of current. On that side it's going down, on this side it's going up. So they are talking about north. North is on that side, that must be going down then. So answer must be option 1, option A. Let's move to the next one now. An electron and a proton are moving along the same direction with same kinetic energy. They enter a uniform magnetic field along acting perpendicular to their velocities. Okay? Their dependence of radius of their paths on the masses is. Okay? So they are entering with, this is the key point here. There is a hint given here, same kinetic energy. So both of them enter with same kinetic energy. So I'll just do that part. I told you that whenever a charged particle enters a magnetic field, it experiences a force. And that force acts as centripetal force always, right? FB is equal to FC. What is magnetic force? QVB. Then you may ask, won't that be QVB sine theta? No. Why? Because they say acting perpendicular. Perpendicular means theta is 90. Perpendicular, the particle enters perpendicularly. So QVB sine 90. Sine 90 is 1. Which would be the case in most of the questions. And that is equal to, do you remember the equation for centripetal force? mv square by r. The centripetal force, no? Which actually causes a particle to stay in circular path. Mass is m, v is velocity, r is the radius. Mass is m. Imagine you are doing a death globe stunt. You are riding a motorcycle inside a death globe. Okay, you are on top of it. Then what? You won't fall down. Why? Centripetal force is there, right? mv square by m is your mass, v is your velocity, r is the radius. Let's cut the common terms out. Tell me what you're going to get. V and V are gone. So I am getting radius from this. Radius is mv divided by qb. They are asking for dependence of radius, but this equation is not enough. Why? They have mentioned kinetic energy in the question. So I must get kinetic energy involved somehow. How can I do that? I can go on doing this. I'll get V from it. What is V now? V is equal to, let QB come here, QBR divided by M. Velocity of the particle is QBR by M. So kinetic energy is given by half mv square, which is equal to half m. What is V square? V square, this is V. Square of it. Square of it. What is square of it? Q square, B square, R square by M square. Okay? And again, let's get the common terms cut. One M gets gone with another M. So what do we have now? We have an equation for kinetic energy which reads like this. Q square, B square, R square by 2M. In school, you have learned this by heart, but I never suggest you to learn it by heart. Whenever you need it, you formulate it instead. You just have to know this concept, that's it. Alright, so it's easy now. I want to get R square now. I have my kinetic energy involved now. R square is equal to 2mk by 2m comes here, no? Q square, B square. Okay? Dependence of radius on the masses. Look at this. I can remove the constants now. What are the constants? 2 is constant. K is constant. Why K is constant? They say same kinetic energy. Same kinetic energy. Electron and proton enter with same kinetic energy. So kinetic energy is also same for both. Charge is same for both. Electron's charge is 1.6 into 10 raised to minus 19. Proton's charge is also 1.6 into 10 raised to minus 19. The only difference is that electron is negative and proton is positive in charge. Got it? But we are looking at the magnitude. Don't worry much about it. And B square is also constant. If all the constants are removed, you could say r square is proportional to m, which would eventually give you r proportional to square root of m. So there in the options, r proportional to square root of m. Okay. Now this is such an important question. So many times such questions have come. This is how you get the velocity radius. You can get velocity from here, even momentum from here. Momentum is mv. Then kinetic energy from here, kinetic energy. All right. Okay, right. So this is what it is. It's an important question, and I'll tell you one more point on this. You can even find, there is another question that is asked. You can even find the time period. How to find the time period? Time period is given by distance by velocity. I said already that particle will execute a circular path, right? Because the particle enters perpendicularly. When the particle enters perpendicularly, the path is circular. Circular path is like 2 pi r. Why? Distance covered in one circle is called circumference of the circle. Circumference of the circle. What is circumference? Perimeter, 2 pi r, right? 2 pi r is the circumference of the circle. Divided by velocity is v, which is 2 pi r by, do you remember what velocity is? Look at this and tell me. Qbr by m, right? Qbr by m. Qbr by m. Qbr by m. What do they ask? Cut this r with r. What do I have now? That is equal to 2 pi m by qb. Show that the time period of revolution when a particle enters a magnetic field is independent of radius or independent of velocity. Yes, time period is independent of radius here, independent of velocity here. You don't see any term that's related to radius, do you? No, no. Magnetic field, no radius, no velocity. So this equation is devoid of radius and velocity. That means radius or velocity have got nothing to do with the time period. Time period is independent of radius or velocity. Same question can come with the frequency also. You know what frequency is? Reciprocal of time period. Take the reciprocal of time period. QB divided by 2 pi m. That is also independent of time period. Sorry, independent of radius, independent of velocity. Right, that's an important question there, okay? Now the same question can be repeated with two particles enter with same momentum. Then you keep momentum constant, or same velocity. Then keep velocity constant. These questions have come in the past. They are very, very important. Okay, let's get to the next one. A charged particle after being accelerated through a potential difference V enters a uniform magnetic field and moves in a circle of radius r. If V is doubled, the radius of the circle will become. So again a Cbse question 2020. Read it again. A charged particle after being accelerated through a potential difference. Whenever you see this sentence, accelerated through a potential difference, you must think of this. You see this in almost all chapters this year. W by Q is equal to V. This is the definition of potential, right? Work done to bring a +1 coulomb from infinity up to the point. Work done per charge is called potential. Work done per charge is called potential. If you cross multiply, work done is equal to Q into potential difference, right? And this is same as kinetic energy, because earlier today I told you work done is same as kinetic energy. Like I said before, imagine you are standing in the middle of a road and a car hits you. Your kinetic energy is same as the work done by the car. Correct? Alright. Or when a batsman hits a ball, the kinetic energy of the ball is the work done by the bat. Okay, or rather the batsman. So kinetic energy is equal to QV. Alright. And there's a uniform magnetic field. It's about entering a uniform magnetic field. What is kinetic energy equation? Just now we wrote Q square B square R square by 2m. That is what I wrote for kinetic energy. Check this out. Kinetic energy is Q square B square R square by 2m. We've just done it. Q square B square R square by 2m. So I'm putting that kinetic energy into this because the question is about charged particle coming out of potential. charged particle coming out of potential, q square b square r square by 2m. Again, the similar terms are getting gone. Q is cut with the q. So that is leaving you with an equation for V. What is V? Q B R square by 2m. That is equation number 1. And in the second scenario, V is doubled. Look at that. V is being doubled. The potential is doubled. So I must write a second equation. Doubled means it is 2V now. Particle is the same, Q, right? It enters the same magnetic field, right? It enters the same magnetic field. But R is different this time. I'm going to call it R dash. The particle will execute a circle of a different radius now. Q is the same because the same particle, right? B is the same because they say that the same magnetic field, right? Then what? Mass is the same because same particle, right? 2 is already same. Then what? Only R will change because V changes, no? When left side changes, somebody has to change on the right side, right? Divided by 2m, equation number 2. Let us divide equation number 1 by equation number 2. What do we get upon dividing? V and V are cut. You'll get 1 by 2 on the left side. On the right side, all the terms. I'm just cutting them on this equation itself. I can't do that, but still Q and Q, B and B, 2 and 2, M and M. All right. So what am I left with? Finally, I have something like R square by R dash square. Cross multiply. If you cross multiply, R dash square is equal to 2R square, or R dash is equal to square root of this is what? Square root of 2 on the right side, square root of this is R. So new radius is equal to root 2 times the old radius. So the answer is option B, root 2 times the old radius. It's an important question again. A particle comes out of a potential. A charged particle comes out of a potential. Similar question you will see in dual nature of matter and radiation also. Okay, so whenever a charged particle comes out of a potential, you call the kinetic energy as work done which is QV. Alright, so you put that kinetic energy here, equation for kinetic energy, into that you are substituting for kinetic energy. Then you get an equation for V. Then you write the second case, then you just divide them, that's it. We have 2 cases and then 2 equations, and you know what to do. You just have to solve them by dividing. Okay, let's get to the next one. In a hydrogen atom, an electron is revolving. In a hydrogen atom, an electron is revolving in an orbit of radius 0.53 angstrom. You know what this radius is? It's called Bohr's radius. Alright, Bohr radius. With 6.6 into 10 raised to 15 rotations per second. Magnetic field produced at the center of the orbit is. Okay. Hydrogen atom. Hydrogen atom is the simplest atom with 1 proton and 1 electron. 1 proton at the center and 1 electron. Okay, no neutron, right? Hydrogen atom is the simplest atom. It has 1 proton at the center and 1 electron revolving around it. Okay, magnetic field produced at the center is. What all things are given? Radius is given. Radius is 0.53 angstrom. But for simplicity, I'm taking it as 0.5 angstrom. Don't worry about that small number. Okay. Just look at the power. It is so large, you know. So it doesn't matter much. Imagine you have $1 billion in your account. So you won't care about the $100 lost, right? Same way. When the power is so large, forget about those small numbers. Okay. So radius is 0.5 angstrom. Frequency is given. Frequency is 6.6 into 10 to the power 15 rotations per second, RPS. Magnetic field produced at the center of the orbit. So magnetic field is given by what? Here the electron revolves in anti-clockwise direction. Just imagine. So the current flows in clockwise direction, right? Because current direction is taken as opposite to the direction of electron flow. If I assume that the electron is going in anti-clockwise direction, the current is flowing in clockwise direction. Okay. So this revolving electron can be considered as a circulating current. Am I correct? circulating current. So this is like a current carrying coil now. Current carrying coil. Imagine I have a coil like this. I just cut it open. I let a current pass through it. The magnetic field at the center is given by what? You have written this in class. Magnetic field at the center is given by mu 0 I divided by 2R. Okay, magnetic field at the center of a coil is given by mu 0 I divided by 2R. Mu 0 I divided by 2R. So let's substitute for everything. Mu 0, 4 pi into 10 power minus 7 into current, I have no idea, I'll find it out later, divided by 2 into radius is what? Radius is given there, 0.5 into 10 power minus 10. Now my next challenge is to find the current. How to find the current? I'll use the concepts of current, electricity here. Okay, so I don't have space here, so I'll just use the other board. Okay, so current is, I'll just find the current. The current is given by Q divided by T. Rate of flow of charge is called current. So I'm talking about a single electron here, single electron. So charge must be E, right? Yes, charge must be E. And 1 by time period is called frequency. Reciprocal of time period is called frequency. Reciprocal of time period is called frequency. This is charge of electron is E. 1 by time. 1 by time is called frequency. Charge of electron is 1.6 into 10 power minus 19 into frequency is given 6.6 into 10 raised to 15. 6.6 into 10 raised to 15. Take 1.6 into 6.6. That's roughly 10. 10. 16 sixes are 96. So that's very close to 100. Correct. So it's like 10 with the 10 power minus 19 with the 10 power 15 will give me what? 10 power minus 19 and 10 power 15. 10 power minus 4 with the 10 power minus 3. So it is roughly 1 milliampere. The current is 1 milliampere. It's a standard value. Okay. So 10 milliampere. So I can put it right here into this 10 milliampere, 1 milliampere, 10 raised to minus 3. I've just substituted for current. I had to find the current. No, that is why I did all these steps. Current is charge divided by time, which is E into F. E is charge of electron, which you know, 1.6 into 10 raised to minus 19. Frequency is given 6.6 into 10 raised to 15. Solve it, you will get the current as 10 raised to minus 3. That means due to the motion of electron, the current generated is roughly 1 milliampere. Now it's done, finished. Look at that. What is 2 into 0.5? 2 into 0.5 is 1. 2 into 0.5 is 1. 2 into 0.5 is 1. Then what? I get what? 4 pi into 10 power minus 7, 10 power minus 3, 10 power minus 10 by 2 into 0.5, 1, 10 power minus 10. And these are getting cut now, leaving you with 4 pi. 4 into pi value is 3.14. That should be 12.56 Tesla. Let's check the options. 12.5 Weber per meter square. Weber per meter square is another name for Tesla. Alright, the unit of magnetic field intensity is Tesla or Weber per meter square. Okay, so let's move to the next one now. Question number 19, that's also very, very important. It can be taken as a standard shortcut. A length L of a wire carries a steady current I. It is bent first to form a circular plane coil of 1 turn. The same length is now bent more sharply to give a double loop of smaller radius. The magnetic field at the center caused by the same current is. So let us analyze the question one more time. You take a wire, a certain length of a wire. This is the wire, okay? You bend it to form a circle. It is first bent to form a circular plane coil of 1 turn. So first case is 1 turn. Okay. Second case is what? You break it open, you wind it more sharply so that there are n turns now. Okay. First case you had only 1 turn. Second case you have n turns. Okay. Now, the magnetic field at the center of the coils is, right, here. This is magnetic field at the center, here the magnetic field at the center. I need to compare them. Alright, so I am writing the magnetic field at the center of this coil. What is the equation for magnetic field at the center of the coil? Mu 0 I by 2R. I have written this already. Look at this, mu 0 I by 2R. Magnetic field of the magnetic field at the center of a circular coil is mu 0 I by 2R. Mu 0 I by 2R, I call it B1 for this coil, B1, okay? And this coil I call the magnetic field as B2. What is B2? It is mu 0 I by 2 into, the radius is much smaller now, I call it small r. But remember, there are n turns, so I must multiply with n. I repeat one more time. For the first coil, the magnetic field at the center is given by mu 0 I over 2 capital letter R. Okay, because the radius of this loop is capital letter R. And in the second case, you are winding it into smaller coil of n turns. Okay, so it is mu 0 I by 2 into, there the radius is small letter r. Small letter r into n. Why? For one coil it is, one turn it is mu 0 I by 2r. 2 turns into 2. 3 turns into 3. 4 turns into 4. N turns into n. Now I need to relate them. That's what. But one thing is clear. The total length of this wire, which is called the circumference, right? Just imagine you are cutting it open. You are stretching it. That will have a length of 2 pi r, right? Circumference of the circle. Circumference of the circle is 2 pi r. 2 pi r, right? Actually, this is also made with same wire. So what is the length there? It is 2 pi r into n. Because one turn circumference is 2 pi r, 2 turns 2 pi r into 2, 3 turns 2 pi r into 3, n turns it's going to be what? 2 pi r into capital letter N. So these are equal. Why? Because they are made with same wire. This wire actually is cut open and you wound it into smaller turns, right? So basically those lengths are same. So let us cut this 2 pi with the 2 pi. And what do you get for small letter r now? What do you get for small letter r now? Capital letter R by n goes to denominator, right? I can put it here. Mu 0 I by 2 into, in place of the small letter r, in place of the small letter r, I am writing r by n. In place of small letter r, I am writing this small letter r, I am writing this r by n into, what is this? That n is still there, no? Last step, mu 0 I by 2r, this n will go to numerator. That will make it n square. This is new magnetic field. You know what this orange circle is? That is something you have seen before. That is the old magnetic field, right? So what do you understand now? The new magnetic field is n square times the old magnetic field. You can take it as a standard shortcut. Okay, you don't have to prove it anymore, but still I thought of doing it. You can take it as a shortcut. If a wire is, it's a frequently asked question, if a wire is cut and rewound into smaller turns, the new magnetic field at the center of the coils is n square times the old magnetic field. Okay, here they say bend more sharply to double loop. Double loop means what? N is 2 loops, right? Double means 2 loops. So 2 square times 2 square is 4. So the new magnetic field is 4 times its first value. The magnetic field at the center caused by the same current is 4 times the first value. Yes. So if it is bent into 3 turns, 3 square times, 9 times. If it is bent into 4 times, 4 turns, 4 square times, 16 times. If it is bent into 5 turns, 5 square times, 25. Right, likewise, you can take it as a shortcut. Now this is actually a shortcut you can use, all right. It has a very high chance of appearing in examinations, okay, coming in examinations, okay. That's very, very important, n square times the whole magnetic field, okay. Let's get to the last question here. Okay, look at that. A proton, if a proton, deuteron and alpha particle on being accelerated by same potential difference enters perpendicular to the magnetic field, then the ratio of their kinetic energies is, okay, proton, deuteron, alpha particle. Basically, there are 4 charged particles which you use in questions in class 12. One is proton. Proton is what? Hydrogen atom's nucleus, 1H1. Second is deuteron. Deuteron is what? Hydrogen atom's isotope deuterium. Hydrogen atom has an isotope called deuterium. Deuterium's nucleus is called deuteron, 1H2. Okay, atomic number is 1 itself, mass number is 2. Then we have a third particle called triton. Triton is what? 1H3. Hydrogen atom has another isotope. Hydrogen has another isotope. Its nucleus is called triton. Last one is alpha particle. Alpha particle is a particle that comes out during radioactive decay, which is deleted now. Alright. Anyway, alpha particle is nothing but helium nucleus. Remember, all these are nuclei. This is hydrogen nucleus. This is deuterium nucleus. This is tritium nucleus. This is helium nucleus. Okay. The question is about what? Proton, deuteron, alpha. They are coming out of same potential, right? When someone comes out of a potential, I told you, hope you remember this. This is what you do. Kinetic energy is given by QV. Kinetic energy is given by QV, right? Because work done per charge is potential difference. Cross multiply work done as Q into potential difference. Work done is same as kinetic energy, right? So QV. So I can put it here. So this question is also accelerated by same potential difference. I had told you that you have to use that concept whenever you see that. Some particle comes out of a potential. Kinetic energy is what? Kinetic energy, you can call it Q times V, right? They are asking for kinetic energy of what? Proton, deuteron, alpha particle. Kinetic energy of proton. What is kinetic energy of proton? Q into V. Charge of proton. This number is called charge number, right? Atomic number or charge number. 1 proton, right? 1 proton. This number tells you that there is only 1 proton. So I can call it E. Proton's charge is E. Potential difference is V. That's equation number 1. This number is called mass number. That is mass, 1m. For this one, mass is 2m. For tritium, the mass is 3m. And for alpha particle, the mass is 4m. But charges are what? 1e, 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 2e. Okay. So let us look at kinetic energy of next particle is deuteron, right? Ah, yes, deuteron. Tell me about deuteron. Deuteron's charge number is also 1. 1. So 1e. Potential is V itself. That is also entering the same magnetic field, right? Oh, same. That is coming out of same potential, right? So first particle comes out of potential V. Even second particle comes out of same potential. Even the third particle would come out of same potential, right? All of them come out of same potential, same potential, same potential by the same potential difference. Look at that, same potential difference, right? So kinetic energy of alpha particle, the third particle is alpha. Am I correct? Yes, alpha particle. So what do you write for it? Alpha particle's charge. Alpha particle's charge. This is called the charge number, right? The number you write at the bottom is called charge number or atomic number. Atomic number, right? That tells you how many protons are there. 2 protons. 2 protons, the charge will be 2e. But potential difference is the same, no? V. Equation number 3. Now they are asking you to find the ratio. Kinetic energy of proton is to kinetic energy of deuteron is to kinetic energy of alpha is equal to. When you take the ratio, I'm going to cut it here. Hope you understand. So E cut, V cut, then you take the ratio. So what are you going to get? You will get like from the first term you will have 1. From the second term also you will have 1. From the third term you will have 2. So the ratio is 1:1:2. Answer is option D. Option D. Okay. Hope it's clear. So kinetic energy is given by QV, then you find the ratio. Okay. So you can take as per the particles. Now let's move to the last question today. An electron and a proton with equal momentum. That is a keyword. They can ask the same question with equal velocity also. A proton and an electron with equal momentum enter perpendicularly into a uniform magnetic field. Perpendicularly into a uniform magnetic field. Okay. Then the path of the proton shall be more curved than that of electron. Path of the proton shall be less curved than that of electron. Both are equally curved. Path of both will be straight line. So, a proton and electron with equal momentum. That's a preset condition. Okay, they say that the momentum is equal. Alright, sometimes they will say kinetic energy is equal. Then you have to involve kinetic energy in the equation. Okay. And if they say velocity is same for both, you must incorporate velocity into the equation. Okay. So anyway, for the time being, I'm just looking at radius. They are asking about the path of the proton shall be more curved, less curved, equally curved. So it's about curvature, the curvature. Alright, curvature. Okay, so let us look at the radius equation. Do you remember the equation for radius? mv divided by qb. We learned it already. You want me to show? See this? I'll tell you. Somewhere I did r is equal to mv by. Look at that. Radius of the particle is, because magnetic force is acting as centripetal force. Centripetal force is mv square by r. Correct? It's equal to qvb. Now cut them out. You are getting r is equal to mv by qb. So I'm going to use this equation in this particular question. R is equal to mv by qb. And what do they say about this? What do they say about this? Let's write for both the electron and proton. So first I am writing for electron. What is radius of curvature for electron? I can write mv divided by charge of electron is E, magnetic field is B. That is equation number 1. Correct. How about radius of curvature for proton? Radius of curvature for proton is, that is also mv. Why don't I write mv differently this time? Because they say that momenta are equal, both having equal momentum, right? Momentum is same means if I put mv for the first particle, I should be putting mv for the second particle also. Correct? mv for the first particle and mv for the second particle. Okay, then what about the charge of proton? That is also E. Don't worry about the signs. Electron is negative. We know that, but still magnitude is taken. Then magnetic field is B. Same magnetic field. Both enter the same magnetic field into a uniform magnetic field. Same magnetic field. So let's compare them. If you compare this, what do you understand? R proton and R electron are equal. Why? mv, mv, E, E, B, B. All are same, right? So if you compare the equations, the right sides are equal, which would mean that the left sides are equal. Rp is equal to Re. Alright. Rp is equal to Re. Okay. So the path of the particle will be, for example, I'll tell you, this is one question. This is the magnetic field. I'll tell you what that means. Look at that. Look at that. This is a particle. First an electron. First a proton enters. This is a proton. Okay. Proton. Proton is positive. Proton is positive. V is to the right. Psi cap. Cross minus k cap. J cap. Right. So that must be, if it enters this, that force direction is upward. So the particle will be going in which direction? The particle will be going in this direction. And let us look at electron. How about electron? Electron enters. I said proton and electron enters, right? Electron. What about electron? Electron will have, proton is positive, electron is negative. That will show in the direction. So for this one, I got the force upward. Did you understand how I got that force direction? We did that in a previous question. Force is Q into V cross B. Q into V cross B. V is Vi cap to the right. B is minus Bk cap. Why? Into the board. Into the board is K cap. Then take I cross minus K. QV cross B. You will see that the force is up. If on positive particle the force is up, negative particle the force is down, down, down. Look at that, the force is down. Now tell me how the path of the particle will be. That will be in this direction. But remember, both of them will have same radius of curvature. Look at the radius of curvature. Look at the radius of curvature. Both will be the same. Both are equally curved. Okay. Same question can come with equal velocity. Then what? Equal velocity means you must put same v for both. But masses will be different. Shall I do that question also? I'll do it. Don't worry. So I'll just do that question also. Equal mass. This is how I do it. Okay. This is how I do it. R is equal to mv divided by qb. So R proton will be equal to same. Imagine they are having same velocity, not momentum. I'm giving an additional question. It's an additional question. Okay. Additional question. Okay. Same momentum, the same velocity. They say, what if they enter with same velocity? In the original question, they were entering with same momentum, equal momentum. But what if they enter with same velocity? mv by qb, right? So R proton, mass of proton into velocity by charge of proton into magnetic field. Look at that. Mass of proton, you have to be specific this time. Mass of proton is mp. Velocity is v. I don't intend to write vp because velocity is same for both. Correct. Velocity is same for both. It's given. So R electron, what do we write? Mass of electron into velocity is v. Charge of electron is e. Magnetic field is b. Equation number 2. Okay. So radius of proton by radius of electron will be what? All the other terms are cut. Velocity cut. Electric field cut. Magnetic field cut. Sorry, electric charge will cut. Magnetic field also gets cut. You get mass of proton by mass of electron. But we know one thing. Mass of proton is very greater than mass of electron. Mass of proton is very greater than mass of electron. Mass of proton is 1.00727 AMU, whereas this one is like 0.00055 AMU. So they are actually not even comparable. Mass of proton is very large in comparison with that of electron. So when mass of proton is more, radius of curvature for proton is also more. Because on the right side, if numerator is more, on the left side also, numerator should be more. So I could say that this implies that if mass of proton is greater than mass of electron, radius of proton is very greater than radius of electron. Okay. Now try the same question. This question was with proton and electron. You can try the same question with alpha particle, deuteron, triton, like this. Triton, deuteron, proton. This is deuteron, this is triton, this is alpha particle. But remember, charges are to be put 1e, 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 2e. Masses are to be put 1m, 2m, 3m, 4m. Right. Try them at home and then leave it in the comment. If you got the solution, just leave it in the comment. And then that's all from me for the time being. Anyway, we have covered almost all questions from this chapter except the moving coil galvanometer part. But these are all important questions and expected questions. Try to practice them again and again. All right. And apart from this, you have to practice other questions as well. But this is like the cross section of the whole chapter. Okay. So you've gone through almost all the important questions. Now I'll come back with another topic, electromagnetic induction, later. So see you again. I'm signing off. Bye. Thank you.